Hi everyone, in this video we want to work on understanding what the basic shapes of the family of exponential functions will look like. So the idea is we want to add those to our list of basic functions. So similarly to y equals absolute value of x and y equals x cubed and y equals the square root of x and so on, as soon as we see the equation for a basic exponential function, we have a pretty good picture in our head of what it will look like, and then we can apply transformations to that picture. So this is a little different because it's not just an x squared or an x cubed. It's kind of similar to when we looked at, okay, well actually x squared and x to the fourth and x to the sixth and so on are all similar in shape. They get a little flatter at the origin as the power gets bigger, and they get a little steeper on the edges as the power gets bigger, but they're very similar, all kind of a parabola looking shape. And we also noticed that with the odd powers, we got something similar to a cubic for x cubed, x to the fifth, x to the seventh, and so on. Same thing, flatter in the middle, steeper on the edges. So the shape was changing somewhat, but the general idea of what it looked like that we had in our head was the same. And the exponential functions are going to work like that as well. So those were the power functions. These are the exponential functions. And actually, it's a really good distinction to make. Here, let's say it right here. Okay, so some fancy math writing here, but what I'm saying is f of x equals x to the p, and I think we could even take 0, but I'll leave it p greater than 1. If you have a power of at least 1, and this says that your power is an integer, you have a power function. And I don't even care so much that you remember what they're called. I just really want to point out that these are definitely not the same thing. An exponential function has a number for its base and a variable for its exponent, whereas a power function has a variable for its base and a number for its power. So these are different and they have different properties, and it's really important that we don't mix them up. So not to be confused. Okay. So I'm just going to give you two specific examples so you can see some of what the shapes will look like, and then we'll talk about how that would change if the base changes. So there is a little bit of a rule about what it means to be an exponential function. An exponential function is number to a variable, but there's rules about that number. In order for it to qualify for the name exponential function, that base number has to be positive and cannot equal 1. And this isn't because you can't make a function with a negative base and a variable power, or with 1 as the base and a variable power. It's just because we're trying to build up a family of functions like the power functions that all are very similar, and negative bases make very different functions than positive bases, much more complicated. And if 1 is your base, it's actually a more boring function, less interesting function. So we're just narrowing it down to bases that are positive and not equal to 1, so that we've limited it to a certain type of graph that we'll see. Okay, so I want to look at y equals 2 to the x and y equals 1/2 to the x. So we can just plot by plugging in some points and see if we can figure out what's happening. So for example, if I plug in 0, 2 to the 0 is 1. So we go through 0, 1. If I plug in 1, 2 to the 1 is 2. So we go through 1, 2. If I plug in 2, I get 2 squared, which is 4. If I plug in 3, I get 2 cubed, which is 8. And what you should be seeing here is that my y value is doubling. Let me go ahead and finish writing the points down. 3, 8. So if you have a base of 2, that means your y value doubles every time your x value increases by 1. We can absolutely look at negative x values. In fact, it's a good reminder of what negative exponents mean. So if x is negative 1, we get 2 to the negative 1, which is 1 over 2. So 1/2. If x is negative 2, we get 1 over 2 squared, which is 1/4. If x is negative 3, we get 1 over 2 cubed, which is 1/8. And hopefully we can start to spot that the bigger the negative number I plug in, the smaller the y value I'll get back. What we're getting over here is asymptotic behavior. So exponential functions, when you look at the whole thing and not just stuff in quadrant 1 like we did for applications, exponential functions can have this flattening out asymptotic behavior where there's a horizontal asymptote at y equals 0. On the right-hand side, we saw that our y's were doubling, and that's just going to continue. So this is going to get steeper and steeper and steeper and steeper. Really steep. Exponential functions grow very, very quickly. They always end up beating the power function. So even if you have a big power here and not that big of a base, and this one starts off growing slowly, eventually the exponential function is going to catch up. They always end up beating out the power functions. So let me actually draw in our horizontal asymptote, if you can see that at all, at y equals 0. So this is the basic shape you're going to get for exponential growth. And we'll get into exactly where the cutoff between exponential growth and exponential decay is in just a minute. But we saw both things, exponential growth and decay in applications, and now we're just looking at a little more of the graph. So exponential growth starts off really near 0, grows really slowly at first, and then it starts to skyrocket and gets very, very steep. If I made this a 3 to the x, the difference you would see is just kind of a skewing like with the power functions. We'd still go through 0, 1. We'd still have the asymptotic behavior, but instead of going through 1, 2, we'd go through 1, 3. And instead of going through 2, 4, we'd go through 2, 9. So similar shape, but it's going to be steeper in quadrant 1, and it's going to flatten out more quickly in quadrant 2. And if you upped it again to 4, it would make it even steeper in quadrant 1 and even flatter in quadrant 2. So all of your exponential growth shapes will be similar to this. The points will change, but it'll look something like that. 1/2 to the x. So this one, we can do the same thing. We can plug in points. When x is 0, anything to the 0, anything except for 0 to the 0 is 1. 0 to the 0 is trouble. It's undefined, so we don't want to do that. But 0, 1 we have. If x is 1, we just get 1/2 for our y. If x is 2, 1/2 squared is 1/4. If x is 3, 1/2 cubed is 1/8. And we're seeing the exact same y values we were getting over here. So we do have asymptotic behavior, but this time it's in quadrant 1. Once again, horizontal asymptote on the x-axis. If we plug in negative values, negative exponents give you reciprocals. So if we plug in a -1, 1/2 to the -1 is going to flip and give us a 2. -2, the negative power will flip it, make the base a 2, and then we still have to apply the second power, so 2 squared is 4. A -3, the negative will flip it and make it 2 to the 3rd, which is 8. -3, 8. And we can see the skyrocketing happening again, but this time in quadrant 2. So these are the two shapes that we'll see for our family of exponential functions, and actually what I hope you're spotting is that they're really the same shape. It appears that they only differ by a horizontal flip. If we flip over the y-axis, they would be exactly the same, and actually algebra confirms that really easily. So let's just say this. Notice that y equals 1/2 to the x is the same as 2 to the -x. So if we're comparing the 1/2 to the x function and the 2 to the x function, the difference is this negative sign in the exponent. If that's attached to your x's, that's a flip over y. So they really are, let's say 1/2 to the x and 2 to the x are horizontal reflections. Trying to decide how I want to say that. Horizontal reflections of each other. So there's really only one exponential shape, but to get us started, we decide which direction it's going to be heading. And we want to make sure, I haven't specifically said that yet, but we want to make sure we know the cutoff. So what happens is if you multiply something bigger than 1 over and over and over and over again, your y values will grow and you'll get this shape. So this is the general shape. for b greater than 1. The closer b is to 1, the less steep it will be in quadrant 1. And it is actually a little bit bigger in quadrant 2. The bigger that b is, the steeper it will be in quadrant 1, and the flatter it will be in quadrant 2. Okay, this one is my general shape for bases between 0 and 1. Remember, your base can't be negative, can't be 0, can't be 1. And again, the only reason for that is because those don't give us the same type of shape. So we're building a family of functions that we've called the exponential functions. They all look like this as long as we follow the rule positive base that is not equal to 1. Okay, so we've got two general shapes that are kind of the same shape, just flipped across the y-axis. Some things to notice. The basic exponential functions, no matter what your base is, have their horizontal asymptote, and it's always at y equals 0. We will apply transformations, so if you do a vertical shift, that won't be true anymore, but the basic untransformed exponential functions always have a horizontal asymptote at y equals 0. They always go through point 0, 1. It doesn't matter what your base is. If it's not 0, which we're saying it's not allowed to be 0, then b to the 0 is always going to be 1. So plugging in 0 will always give us 1. Plugging in 1 will always give us whatever our base is. So those are a couple of easy points. I hope you don't have to think about that as a memorization because we'll have a formula, right? So if we know that it's 2 to the x, we could just plug in 0 and 1. But it is nice to notice that those are some really easy points to snag. What else do I want to say? Let's say domain. For either one of these, the domain is all real numbers. There is not a number that we're not allowed to use as a power. So there are numbers that we don't want to use as bases, but there isn't a single number that we're not allowed to use as a power. It can be positive or negative. It can be a fraction. It can be a decimal. It can be a big number. It can be a tiny number. We can do any of those things. Range is always y greater than 0. Again, if we perform transformations, if we do a flip or a vertical shift, that's going to change, but the basic exponential function always has range y greater than 0. Not equal to. It's legal for functions to cross horizontal asymptotes, but the ones we've run into so far do not. So our reciprocal 1 over x and 1 over x squared functions do not cross their horizontal asymptote, and neither do these exponential functions. We will see some trickier rational functions at the end of the quarter that can do that, but nothing we've seen so far crosses its horizontal asymptote. Let's see if I have anything else that I want to say on that. I think that's my list of things to notice. So when you're graphing a transformation of an exponential function, just like with the reciprocal functions, make sure you always follow the horizontal asymptote and draw it on your final graph. That's really important. And I will be checking that on the test to see if you're doing that correctly. All right. Thank you for watching.